Governor. We have Richard Cameron, Governor. Chris Frawley, Governor. Adrienne Matani, Governor. Adam Moons, Governor. I don't think Adam's with us tonight. Erin Dobson is our Secretary this year. Chris Budge is our Treasurer. As I said earlier, I am the President-elect, and Abby Saunders is our past President. I'd like to call upon Erin Dobson to welcome the guests for this evening.
Thanks, Dan. So tonight we welcome the following guests: Eric Hilkes, Stephen Menke, Jay Moore, Ben Robinson, Abraham Jabatondry, George Passon, Peter McClure. Thank you.
Thank you very much, Aaron. And I'd like to call upon Celine Barbeau to welcome the new members.
So the new members that joined the Ottawa-Valley chapter since our last meeting are Alex Cashman, Tim Sutton, David Chabot, Harrit Singh, Andrew Young, and Pearl M. Joseph. Welcome.
Thank you, Celine. And tonight's theme is students and student activities, and I'd like to call upon Peter Shawwood, our Chair of Student Activities, to speak a little bit about that.
Thanks, Dan. Yeah, so this is the first meeting of the year that we have, and so it's really nice that we have this, reference student activities. Tonight I see a lot of students here, which is great. Can I get a show of hands? Like, probably about 10 here tonight, which is really nice. It's really good to see that you guys are coming out to these. It's certainly nice to have, we've got the presidents of Algonquin and Ottawa-Valley here, so very, very good. In general, I mean, the activity that we get from students here, it's a chapter-wide thing. It's not any one person that's responsible for it. The culture that we have in Ottawa is sort of, what can I do for students, not what do I have to do. And that's really something that makes it so that we have people that we do. Really looking forward to this year with it, and I thank everybody for the promotion that we have for it and just the culture that we have. Thanks a lot.
Now, I'd like to also speak a little bit about research promotion. I call upon myself, except I'm already standing up here. So, as many of you know, we raise funds for ASHRAE Research Promotion. This funds research in our HVAC world. Typically, for every dollar that we raise, we're able to invest $2 to $3 into ASHRAE research. And that money that we raise in Canada stays in Canada. So you may have been approached by Abby this evening. She's raffling tickets to the October 27th Red Blacks game against the Hamilton Tiger Cats. And they are club level seats and a parking pass. So anything that you could donate to cause would be greatly appreciated. And if you haven't donated yet, please see Abby. Now we have two tabletops this evening, and I'd like to call upon Noah Goddard from Ottawa to speak a little bit about his.
Thanks, Dan. This was very unexpected. So I appreciate you guys having me here tonight. We decided to have a tabletop tonight because obviously our incentive program lines up quite well with the topic. And I've had a chance to talk to many of you in the room throughout the year, but if you haven't already, I'd love to hear from you regarding our incentive program. Basically, any kind of projects that you're doing with commercial customers to save energy, we can help fund that. It's free money, and we've got a whole team here to support you guys. So I've got some brochures and some cards on the table there. Please stop by and grab one and give me a copy. Thank you.
And then I'd like to call upon Clark Campbell from the Limo to come up and tell us a little bit about his talk.
Good evening, everybody. Tonight I'm showing off a couple of new products for Limo. We started a sensor line in April, so we have a full line of CO2, humidity sensors, temperature sensors, pressure sensors available now. They're all NEMA 4 enclosures and come with the standard Blimo orange, right? The other product we brought out this year is a brand new actuator for butterfly valves. It's been designed for the new butterfly valve we brought out, so we can do with this actuator up to a 12-inch butterfly valve. It's available in universal power supply. We also offer electronic fail-safe versions of it, and the modulating actuators come standard as backpack. So all the features you're looking forward to, and it also has near-field communication, so you can program it with your iPhone and or Android. Okay, thank you. Stop by and take a look.
Thank you very much, Claire. Now, I'd also like to call upon Paul Piper. We have a unique opportunity to have Paul here to talk about ASHRAE technical committees. For those of you that don't know what technical committees are, this is a very interesting opportunity to learn a little more about how ASHRAE provides to all of the members and to the members.
Alright, hello everybody, can you hear me okay? I'm just going to take about 5-10 minutes or so. As Dan was saying, my name is Paul. I'm currently with the Master Group as the Director of Health Products for them. Prior to working with the Master Group, though, I was on the manufacturing side for about 20 years. In working on the manufacturing side, I got involved with HRI as well as ISO and with ASHRAE as well too. So on the ASHRAE side, I was past chair for TC55, which is air and recovery equipment, and TC812, which is testing equipment components. As a result, I just wanted to share how, kind of my experience and how you can be involved as well too. Technical committees with ASHRAE, there's 3 big types. Technical committees, which is the main one. There's also task groups and technical resource groups. Those are formed for specific topics, and multi-MTGs are where you have multiple TCs that kind of want to work around a certain problem. So they're kind of temporary, they form, and then they tend to disband. But TCs is what we're here to talk about. If you want to become a member, there's 3 types of members for TCs. There's voting members, there's corresponding members, and provisional corresponding members. If you want to be a voting member, you need to make a commitment really to be at the meetings because that's because you're voting. In order for work to get done, you need to maintain quorum, you need to follow Robert's Rules of Order, all of that. So if you want to be there and you commit to be there, you can become a voting member and be part of the committee that way. However, if you're not going to be there every single meeting or even at any of the meetings, you can still become a corresponding member or provisional member and contribute to that technical committee. People who come part of the committees tend to like to be balanced, so they look for people from all different areas in the industry. If they're a manufacturer, a representative, or some university, or an owner, or an end user, students, whomever, there's a variety of different people who can participate in committees, and indeed they look for as many different types of people as they can. And honestly, it's a volunteer organization, so it's on your own time. Nobody's going to say no if you want to contribute. That never happens. TC is set up. I'm sure you're familiar with how the local chapter is set up, but the TC is set up through TAC, which is Technical Activities Committee. There's the chair for the committee, and then there's the officers, which consist of the vice chair and the secretary. So if you do want to commit to be part of a technical committee, each one of these terms is basically 2 years. So if you want to become chair for a committee, normally you do 2 years as secretary, 2 years as vice chair, and then you do 2 years as chair. There's occasional exceptions, so you can extend it by an additional year, depending. That's usually the way it goes, and that's usually after spending a bit of time around the back in the peanut gallery. You attend meetings, and you show they're going to show up, and then you can become an officer. My experience with TC812, which is a very tiny committee, with a bunch of wizened veterans that had chaired that committee numerous times, and couldn't find another chair who was in his 3rd year. I was a young kid coming out, I was sitting around the back, and I said, look, if you need somebody, I'll do it, but I don't know anything compared to what the experts in desk communication have been doing this since before I was born. And they say, no, you don't need to know any of the technical, you don't. You can participate. So I was there for 1 year, less than a year, and I became chair of TCA 12, so dreams can happen. Other than that, there's different areas that you can attend. So again, those are the members, but again, corresponding members, these other different areas are also of interest as well too. So you can contribute to subcommittees for handbook, for research program, standards, and then other little special tasks and things that you can do. One example for research, so really the key is to find something that you're interested in. I'll show you the links where you can go. I'm going to leave this presentation for the chapter. I embedded some links into it, so just click through. You don't have to find it all on the website anymore. But in this case, so for research is one thing you can do. So research has its own subcommittee. Research is generated within the technical committee based on work that's done. Let's say clarifying an issue in the handbook. Let's say something becomes interesting out of the program, or a particular standard needs some clarification. Research is there to kind of provide that clarity. You can participate in that. If you're more in a scholastic kind of background, if you're doing a master's or PhD, people tend to gravitate towards research on the subcommittees from those areas. The other thing you can do is also participate in standards. So if you're doing stuff in your day-to-day, you deal with a particular standard often. Maybe not one of the big ones like 91 or 62, although you can certainly participate in those. But they're extremely time-consuming. You're going to spend any amount of time. But there's lots of small standards. A good example here is Standard 84, which is the standard that is the cognizant TC is TC 55, which is my old TC. And that's the method of test for testing air heat exchangers, essentially. So you can participate in the standards process as well. You can do studies. There's all different little activities that come out of standards that can be done. If you want to contribute to handbook, you can do that as well. It can be anything from, if you're not very experienced, let's say a student, you can contribute to the grammatical level, formatting level, consistency, just to get kind of your ground into it. If you have more experience, you can write and contribute certain portions. If you're a manufacturer in this room, potentially, maybe there's an area that you want to work on that you want to make sure is represented correctly, technically within the handbook. These are the places that you can go to do that. And all that can be done at the subcommittee level. All of it can be done remotely through the program as well. Program is something else that you can do as well. If you are, let's say, in this room, let's say consulting engineer, you have an interesting project. Certainly there's ways on the grassroots level, at each chapter level, that you can get your work recognized. There's prizes and things like that, but those prizes, those projects, regardless, could be turned into a seminar for a program. You can write a little paper on it, you can present it at a conference that's convenient for you, if it's a summer meeting or a winter meeting, and you can show your work to the world at large that attends that as well. So there's lots of different areas, and that's usually fairly easy to do within the TC. So how do you get involved? These are the ways that you can get involved. I put all the short URLs here for each one of these different areas. If you would like to contribute to a TC on the technical side, I'd say go to this link, look at all the TCs, see what interests you or what your area of expertise is. I guarantee you there's a TC that covers that. Based on those, you can find the scopes, which are all available here for each of the TCs. So some of the titles might be misleading. You can dig into a little bit more detail. And all of the TCs do have their own websites as well. So you can dig into that. You can look at past programs. You can read past minutes. You can see who's part of that committee as well to see if you're going to fit in with that group. If you're a YEA member, we have some students here tonight as well. There's a specific document that ASHRAE created for you to be able to participate more easily. But you can get involved any one of those ways. If you do go to the website, want to get involved, you can email the secretary, the chair, or the vice chair. They'd be more than happy to answer your questions or add you to the role. Or you can follow this particular link, which will take you to the online provisional corresponding member form. So you can fill this in with the committees you'd like to be interested in. You can use up to 3 in that particular spot. This is the full URL if you want to follow that. But if you go to an individual TC website, they will have a link to join, and it will take you to this page as well too. So you can also participate through that. One thing I could suggest too, if you do want to get into a TC fairly quickly, you want to be involved, you want to volunteer, it is good if you can make one meeting in person, introduce yourself to the chair, to members of the committee, get a feel. Not all committees are created equal. I've been on some very good committees. Very dynamic people, very interesting people. I've also participated in other committees that are not so much fun. Very small, very dry, very boring, nobody does any work, it's just really painful. So it's not bad to attend a committee, see what you're going to be involved with, and then from there you can ask to participate, and you, from then on, you don't really need to participate. You don't need to be present at all if that's going to be an issue with your employer or with your personal finances. So remote participation, one thing ASHRAE does not do great is remote participation. Once you're on a subcommittee, most subcommittees do have interim meetings, and they'll do that by WebEx and show documents. And I'm on SPC 84, which is the standard still. And there are regular bi-monthly meetings on that to review the standard, the wording, the documentation. So that typically happens. If you want to attend a TC meeting though, it's not common to have a remote TC meeting where you can dial in as it's happening. That's not there yet. ASHRAE is committed to do that moving forward, so we will see that in the next couple of years. But right now, that really doesn't happen. But like I said, remotely, subcommittees is the place to really participate remotely. If you want to be on a committee, you need to commit to being there at least one out of every 2 weeks. And that's pretty much it. So it's been a great experience for me, and I really enjoyed my time with TCs. I still participate. I'm there once a year instead of twice a year. I'm not a voting member of the committee anymore, but over the past 10 years, I've made some great friends, great competitors that have become friends as well over the years. It's just been a very positive experience. If you want to get on the technical side of ASHRAE, this is a really great way to do it. So that's 10 minutes, but pretty much done. Any questions at all on TCs? If not, you can come see me afterwards, and I can answer any specific questions you may have. So thanks for your time.
Thank you very much, Paul. Yes, again, what a great way to get involved. With that, I'm going to wrap up the first part of business as we have dinner. And please, again, if you haven't donated to ASHRAE OVC, please graciously. Abby will come to you. And for those of you who only have a plastic, there is actually a bank machine inside. So, no excuses. Thank you. Okay, everybody. Dinner's going well. We are going to move on to the evening events, and I'd like to begin. I regrets I failed to call Joe up earlier to discuss the event. So Joe, if you can come up now, please, that'd be great.
Hi everyone, I'm Joe Delval. For those who don't know me, I am the YA chair for this coming year. I'd like to thank first of all the people who did enter the contest, the leadership weekend and the leaders contest. We had 5 participants in the leadership and 2 in the leaders. Unfortunately, we didn't win either. So there'll be another contest coming up shortly for the next session, which will be the next year. I've also talked with Adam about us sponsoring as a chapter someone to go to leadership weekend, and that's going to go as well. It hasn't been discussed fully yet, but there will be some sort of internal contest between members here who are interested to do that. Next on it, I have a event coming up on the 3rd of November. That's a Friday at 7. We're going to be doing archery tag. So any of those who are interested or did it last year, there'll be about 20 spots, I think. I might make it a 2-hour event depending if we get a lot of participation. So if you are interested, I'll be sending out an invitation for that at the end of this week. Thanks again everyone, and hope to see you out.
Thank you very much, Joe. I would like to call upon Abby Saunders as we will now draw for the ASHRAE OVC raffle. Does anybody still need to buy tickets? So these tickets were graciously donated by Water Niagara Ottawa Control. And again, they are for 2 tickets to the Ottawa Red Flags you know, just draw it. So the lucky ticket is blue. 8, 3, 6, 9, 1, 4, 9.
9149?
Yeah.
9149.
I think that might be.
That might be yours. It looks pretty close to me, so I think that's a winner. $820 raised tonight for ASHRAE OVC. So as Abby said, that's tied for a record. Fantastic work, Dave. And if they take a couple of pictures, again, it is a blue ticket. 8, 3, 6, 8, 7, 4, 7. Fantastic. Thank you very much, Abby. Thank you very much, everybody, for your So we'll now move into our program portion of the evening. And in a minute, we'll call our speaker but tonight's topic is electrical fundamentals for HVAC for life. So as many of you are aware, I mean, we're predominantly in HVAC in our market. We require electricity to, well, make all of our stuff work. Now, quite often there are many different electrical options, there are many different choices that need to be made. Jeff is here to walk us through some of these options and what the differences is and why these differences matter. Why paying attention to different voltages, amps, some other strange words. Why these matter to us, why they should matter to you, and what the long-term consequences can be if we don't pay attention to them. So without further ado, I'd like to actually call upon Chris Brawley to introduce Jeff.
First of all, I would say that everyone can kind of pulled into things on a very quick basis, sort of helping out for other people doing things that are very, very important to them. So Dan, it's been going very smoothly, and we appreciate your efforts and warm up for your future term.
Thank you very much.
So what I was going to do is introduce Jeff's background. And how this talk came about is I'd asked him when we were elected, because I find a lot of mechanical people or background in mechanical, we have a passing sort of knowledge of electrical, but we don't tend to have deep, knowledge with any depth that counts. So anyway, background in general. He started out his career as a marine engineering officer with the Merchant Marine. He then joined the land electrical engineering as a technical specialist in the service department of Federal Pioneer. Jeff's career continued with other manufacturers and construction, and we worked with positions such as a field service supervisor for Siemens customers. During that portion of his career, he was project manager perception, what you're willing to kind of put up with, and what you think is a good position. Anyway, Jeff had his fill of it for a little bit, so he figured it was time for a change. Okay? I don't know if any of you know Chuck Wood from Cincinnati, but Jeff used to do some reports on electrical systems and go in and analyze things and sort of write up the report. So Chuck had noticed that his reports were pretty good quality, and Chuck convinced him to join with him. Now, something about the promise in terms of how he got on there, so that we would explain things like maybe how the hours are going to be simpler, just 9 to 5, travel, overtime, and that they have beer was served with design coordination meetings. And I did a few meetings with Chuck when they were waiting for a job or working and that kind of thing, and it proved very good beer. It's a good way to spend the afternoon. Anyway, that he was enticed over to Woodman, and he ended up liking it so much that he got both a consultant and stayed there all along. He's currently at Morrison Hirschfield, and he has a background for a CET designation. He also has a limited license from PPO, and he's designed and done energy management, power generation, certified systems, and I know Dan now is mean, but it's very small. Just doing this for a class. Anyway, he's been in the design side for 27 years. He also likes to teach, and he's regularly involved giving a course about the college. And that's current courses somewhere around 4 to 6 on Friday afternoon. So you're going to see that a pretty good dedication being able to pick up that time slot. And everybody else is kind of thinking about it. So, ladies and gentlemen, I'd like you to have to join me in welcoming Jeff and giving us his private conference. Thank you.
So I'm not big on microphones because frankly I don't need one. Learned my volume from, well, if any of you associated with Chuck Wood, you know he had capabilities with volume. A lot of volume. And Chuck and I would go at it pretty good at times. That being said, I think he's forgotten more about electrical engineering than I ever hoped he'll know. Let's get this going. So, tonight, I'm hoping to be your guide on a little safari through the deepest, darkest world of electrical. And as a good guide, I'm going to teach you a bit of the language. I'm going to teach you what you need to do to survive in the jungle, and hopefully thrive in the jungle, if I can get the jungle working. Searching for what? Yep. I may be electrical, but I hate computers. It's okay, it'll come up in a second. Put it back to sleep. So while we're waiting for the electronics to catch up, tonight's not going to be just about sitting. Okay, there's going to be a few little demonstrations that are going to be interactive. And I'm going to be asking for volunteers. Okay? Don't worry, it won't hurt. You might lose a little dignity, but that comes back. Now, earlier today I was reviewing a set of drawings for a project I'm working on. I was looking at mechanical drawings. Okay. And mechanical had a beautiful schedule of all the motors with the fans, the air handling units, all that kind of stuff. It was awesome. Except for the fact that all the voltages were different than the voltages on my schedule. Now, I've got practicing consultants in here, right? Can I get a show of hands on the number of people who are specifying this kind of stuff? Okay. So if my schedule goes out with one voltage and your schedule goes out with another voltage, what happens later on in the project? I heard it. Change orders. Yes. Have I got any contractors? Yes. And what do you think of change orders?
Money in the bank?
You're welcome. When I was a contractor, I loved them too. I made a fortune on change orders. So, unfortunately for you, a lot of what we're going to talk about tonight is going to be how to avoid having so many change orders. All right, here we go. That wasn't too painful. As I said, I'm going to be your guide. We're going to travel through the electrical jungle. And the first step, whenever you're traveling in a place you don't know, you've got to learn the language. We're going to start off with that. We're going to learn a bit of the language. Now, I know you've all had courses on electrical. I teach you a little different, okay? And I want you to keep this in mind. Electricity is nothing more than an energy delivery mechanism. Okay? We don't drink electricity, okay? We don't use it directly. We use it to deliver energy, and we need lots of energy, long distances, very efficiently. Well, we do when I do my job right, okay? So, despite the fact that there are electrons and we're moving electrons around, all of these words we're going to talk about, at the end of the day, are just about shifting energy. And I'm going to show you how that works. So you're going to hear us talk about volts. Well, volts are electrical pressure, a measure of energy that is contained in the electron that we're shoving through the wire. Amps is that flow of electrons. All right? So you've probably seen graphics at times that show pictures of a tank. As a matter of fact, I've used them myself. Okay, and we'll have the fluid inside the tank, and the fluid in the flow is our electrons, and the pressure in the tank is the voltage. So, and then the little nozzle at the bottom of the tank is the resistance to that flow, because it takes pressure to push the electrons along. And we care about all of this because of this, power, energy. And power in watts equals volts times amps times power factor, and folks, let's just leave power factor alone. I can do a whole presentation just on power factor. Okay? You just leave that to the electrical guy to deal with. He may ask you questions about capacitors for large motors and stuff like that, but we're not going to delve into that tonight. What we are going to delve into is AC and DC electricity. Because I need you to understand this so the rest of it makes sense. And I know a lot of you already have a good understanding of that, but bear with me here. So DC is direct current. Okay? And direct current is typically a battery, pushing electrons one direction through a conductor through a load. And that seems pretty straightforward. But we're going to do a little demo. And I need 8 victims, helpers. I've got 8 tables. Can I get 1 for each table? Come on, don't be shy. I'll start picking. I'll start. You're first, because you tried to volunteer somebody else. Come on. This is the easy one. You might want to rush to volunteer. This is the easy one. Okay? You're my battery. Yeah. Hello, battery. All right, so I need 1 person at the far end. You're in just the right spot, and I need 3 people on either side. Okay? Yep, just make a line for me. Okay? Come on, where's the rest of my people? I find it hard to believe you guys are shy. Hello. Please. Each person take a glass, please. And a glass. And, all right, I need you 3 guys over here. Okay? All right. This is a DC circuit, right? And right now, I'm blocking the DC circuit. I'm in the way. So I'm going to get out of the way, and we're going to close the circuit. So what I need you to do is pour a little water in each glass. Just a bit of water. Okay? That's enough. Pass the glass to the next guy. Pass the glasses around, please. Keep going. Just keep passing the glasses around. No, you keep the pitcher going. Okay? When the glass with the water in it gets to you, pour it in the pitcher. So just keep filling the glasses up as they go by. So this is a simple DC circuit. Think of the water as the energy, and we're delivering the energy to the load at the end. It's that simple. It's not complicated, and it's sequential, and it moves around. All right? So this is the simplest form of electricity we do. But it does get a little more complicated. And they're not nearly fast enough, because this should be happening at like 75% speed of light. It should just be a blur. You shouldn't be able to see anything. Alright, that's good, guys. Thank you. But you don't get to leave. You got to hang around for a minute, okay? So, can I get you to step to one side so I can pull up the next screen? Alternating current. Alternating current, instead of going around in a circle, it goes back and forth. And the biggest question I get every time I do one of these presentations is, it goes back and forth. How can it possibly deliver energy? How can it do that? Well, we're going to do the same dance again. So can I get you guys to go back to the same spot? Okay. Now the difference this time is that you don't let go of the glass. So, when he pours a little water in your glass, you pour a little water in the next guy's glass, and so on and so forth, but it's going to go back and forth. So you pour in him first, and then you pour in him, and then you pass it along the same direction. So instead of going sequentially, it goes both ways at the same time, but your glass never leaves your hand. Wow, dead battery. And now, you're an alternator. Alright? So you pour a little in his glass. Alright? You pour a little in his glass. And the same thing at the other end, guys. You're not switching glasses. I saw that. That's a cheat. Okay? Alright? And this is how AC power moves energy. Despite the fact that the electrons are merely going back and forth in the circuit, we're still delivering energy. Now, I was going to do the next step on this where we demonstrate polyphase power, so I was going to have like 3 separate loops up here, but then I realized there weren't enough people in the room, and besides, it'd probably get messy. Okay? So, are we clear on how electricity is moving energy around now? Good. We're good? Yeah. Can you just put the glasses back for me, please? Thank you, because that's the test drive for this. I figured if the mechanical guys could get it, I could use it for my civil engineering students. Thank you to my volunteers. So, in the AC circuit that we had going here, that was a single-phase circuit. And you'll hear that discussed when you talk to the electrical guy. They're always talking about single-phase, or they're talking about three-phase. And the question becomes, if we got a single-phase, where the heck's two-phase? So first of all, there isn't such a thing as two-phase, so don't go there. We just skip that, okay? So, a single-phase system, typical residential single-phase system, will be a 120-240 volt system. Most of you folks, all of you folks, will have something like that in your home, all right? And this little symbol here just represents a transformer, and of course the waveforms represent AC electricity moving through the wire. So, in our little loop we had going up here where we were doing the AC version of it, that would be equivalent to a 120 volt circuit. If I had two loops, that's equivalent to a 240 volt circuit. Okay? And they would be directly opposite each other. 240 volts is a great way to deliver low levels of energy. We love 240 volts for appliances like stoves and stuff like that. But we don't love 240 volts for what you guys do most of the time. Large motor loads means really high current at 240 volts. And it means special starting features for the motors that are a pain. And I've got a little demonstration for that. And I need one victim, a volunteer. And Paul? I can boss Paul around. So, you saw how the AC, the glass is moving back and forth, right? So when it moves back and forth like that, it makes a magnetic field inside the motor, and it makes the motor turn. But in an AC system, the field is going back and forth. Hold it. The field is going back and forth. So it's just doing this. Okay? That's not going around in circles. That's the motor just sitting there making a humming noise and buzzing and getting hot. The shaft isn't turning. So we have to put a special device, typically a capacitor, to change the shape of the magnetic field so it does this. And that capacitor, on a small motor, your little table saw you have at home, it's a little blister on the side of the motor. Okay? Small motor works great. Small motor, small blister. 500 horsepower motor, yeah, no. Okay? It would be huge, and we don't want to do that. So, what we do is, we move on to, we're not doing 240 volts for your typical office building. We move on to three-phase power. And three-phase power in that AC model I was using up here would be 3 of those loops separated by 120 degrees. And three-phase power does some really cool stuff. We have typical 120, 208 volts. We have 277, 480 volts, 347, 600 volts. But the best thing they do is it immediately produces a rotating torque without any special devices. And it's volunteer time again. Who wants to volunteer? I need 2 volunteers. Yep, you'll do. Anybody else? Come on, be brave. It involves holding hands. I know that's scary. Okay? No? No? All right, thank you. So I want you to put your hand on top of my fist. Okay? Just put your hand flat like that. Think we're playing baseball. Okay? Now, stand closer. Just a bit closer. Okay. So, you know how you have that back and forth motion? Okay? You're 1, you're 2, I'm 3. So when I call 1, you pull your hand towards you. So you pull, like that. Now you pull, and I pull, and all of a sudden, we're going in a circle. And I didn't have to use a starting capacitor or any other device to get it turning. And when you're dealing with a big motor, as you'll see in a few minutes, that initial starting like that, we can generate a huge amount of torque, which means we can get that big fan you want going. Now, 3-phase power for a motor like that makes it easier for me to balance the current, which means I don't have underutilized equipment. I don't have equipment with 1 phase that isn't carrying enough load, which means I can put in smaller equipment, which means I can make my electrical room smaller, which means you can make your mechanical room bigger. It also means I'm bleeding less energy off into my electrical room, which means you don't have to get rid of as much heat. And we'll talk about that more in a minute. This is a 3-phase transmission system. This is a 3-phase distribution system. What you're watching here is 3 groups of people with water glasses moving their hand back and forth, filling water glasses. And this is what it actually looks like. So someplace, Niagara Falls, Chats Dam, Darlington Nuclear, there is a generator that is producing 3-phase power, and then there's a 3-phase load, and this is my 3-phase motor over here going around. This is exactly what it looks like. This is the ultimate simplification of a 3-phase electrical grid. And this is the jungle that me and my colleagues work in. And this is the jungle that I want to take you through. So, now that we've learned a bit of the language about what 3-phase looks like, and volts, and amps, and watts, and ohms, we can talk about some of the equipment that makes up this jungle. Now, this slide makes reference to 480 volts AC because, frankly, I stole it from an American website. 480 volts is the standard voltage in the US for large distribution. Okay? In Canada here, in most jurisdictions, we still use 600. And normally right about this point in time, somebody sticks their hand up and says, wait a minute, I see 575 on all my stuff. So 575 volts refers to a motor rating that says that that motor, if it is receiving 575 volts, will still produce full rated horsepower. So when you give it 600 volts, it's more than happy. It's kind of like the lower threshold that will work properly at. You go below the 575 volts, if I don't do my job right, tap the transformer correctly, okay, then the motor doesn't have enough voltage to drive the motor, it'll overheat, you won't get the rated power out of it, the fan doesn't turn right. This is the main switchboard. This is where the energy is coming in from the utility. Then it gets moved around to various devices that keep breaking it down and shunting it off to other spots where you're, in most cases, going to use it. All right? Now, what you're particularly interested in is things like this. This is a motor control center, and this is sending power to the motors to control the motors. So a motor control center we'll talk about a bit more in a few minutes. I got some pictures and stuff like that. But this is what the jungle looks like. This is what somebody like myself is going to design, and then I have to find a place to put the stuff, and then I have to talk to you guys about what the loads are going to be. And half the time when I am trying to figure out what the loads are going to be, they haven't even finished the design on the building yet, and you haven't sized the air handling equipment yet. So I guess based on watts per square foot, what the building's going to be used for, and I make informed guesses, and I pray that I'm going to be right, because this stuff is very difficult to change later. If my motor control center is set up for 600 amps, and this is a true story, if my motor control center is set up for 600 amps, and you come back to me and you say, yeah, Jeff, sorry, but yeah, we're going to be bigger than that. If that's already on site, where's my contractor friend? He left. Anyways, if that's already on site, you can't retrofit it. You can't add another conductor inside of it. You're buying a new one. Oh, there he is. Okay. So, you're tearing the old MCC out. You're putting the new MCC in. It's taking you 12 weeks to get the new MCC. And he's writing you for a new MCC for disposing of the old one. You might be able to get rid of it with a small, say, 25% restocking charge. New conductors to feed it. Oh, and yeah, delay claim. So it's really important when the electrical guy starts talking to you about what he's doing in the jungle, that you give him a degree of certainty. So I had a project quite a number of years ago where it was a facility that only got shut down very occasionally. They knew they were doing the installation of a big chiller, and there was going to be cooling towers up on a roof. Part of my job was to take advantage of the upcoming shutdown and put in a breaker and cables in an existing switchboard to supply the MCC for the pumps that were going to run the glycol, cooling water, I don't know, something in pipes up to the roof. Nice mechanical guy gave me my loads. My loads came out to around 275 amps. He suggested a 300 amp motor control center. I wasn't feeling trusting, and I put in a 600 amp motor control center. Because remember, I'm talking about a facility that they literally shut this switchboard down once every 2 years. So when the time came to actually implement it, I think the motor load came out overall to about 540 amps. And this is why electrical guys throw themselves off bridges for grouchy when you talk to them. Okay? So when you're talking to the natives, give them a degree of confidence on what you know and what you don't know. Because they can help you if they understand the degree of confidence you have to avoid this kind of stuff. This is a physical representation. Okay? Being nice natives, we do symbology, and we have our little worship sections at the single line diagram. And the whole idea of the single line diagram is just to reduce the complexity of actually drawing all these big boxes into something that's like a road map we can read. And it represents the conductors in the system, and it has a language that's associated with it that I'm not going to try and teach you all the language, but wait a minute, we already talked about volts and amps. And look what I've put on here. I've got volts, I've got amps, and I've got what I'm feeding. So you can now read a big chunk of what's going on here. So when the electrical guy sends you his drawings for review during the project, do take the time to look at this. Because if you've just been a really good, diligent person and sized everything for a 600 volt system, and he sends something that says 480 all over it, it's probably a good time to ask some questions. Or when he's putting loads down here, see the little M? So you've got an M with 300 horsepower, and normally we'll put the, this is the chiller, whatever. And you see, oh, it's a 300 horsepower. I don't have anything 300 horsepower on this job. What's that guy smoking? This you should look at. It'll help. Okay? Now, we were talking about voltages earlier. And the question is, how do we get all these different kinds of voltages? We get all these different kinds of voltages with things like this. It's a transformer. Essentially, it's a magnetic device that allows us to change from one AC voltage level to another. And what do you need to know about that magnetic device? You need to know it gives off heat. It's got to be ventilated. It absolutely gives off heat. And anybody who tells you they've got a perfect transformer, please refer them to me, because I want to invest in this miracle. Because I know it doesn't sound like a lot when you say 2 to 3% losses for a transformer, but that's 2 to 3% every hour of every day with the transformers turned on. So what that means to somebody like me is, if you have a large load and you're trying to supply it at a low voltage, besides the fact that I'm going to have to use big conductors, because I have to make the conductor bigger to carry more current, the power equation we were dealing with in the first place, as you increase the voltage, I can get away with less current. If you reduce the voltage for the same power, I have to increase the current. Every time I have to increase the current, I've got to make the conductors bigger. Conductors are copper, most of the time. And even when they're aluminum, they're still expensive. And they take up room that should be for ductwork, right? So, a transformer is not a perfect machine. We've got to ventilate it. And when they're fairly large, that is to say, if you came to me and you said you want to run your big chiller at 208 volts, and it's a 500 horsepower chiller, and I have to use a transformer at 1000 kVA, heat load of 20 kilowatts, when that transformer is operating at full load. So you've got to get 20 kilowatts of heat out of that room. So we try and use a higher voltage all of the time to avoid having too many transformers. So if I get a big load, I want to use a high voltage, I avoid a level of transformation, I avoid having to get the heat out, because how do we get heat out? How are we going to remove heat from my electrical room, typically?
Exhaust fans.
Exhaust fans. So what do exhaust fans need? More power. They need power. So I have to spend energy to get rid of heat, wasted heat energy, okay? So if the exhaust fan is running, and it's probably running a lot, your client is spending money to get heat out of the room that we could have avoided if we had used a higher voltage, because we could have then avoided a transformer. Tips on ventilating the transformer. We're going to remove the waste heat. Okay? Yeah, I see, well, my favorite is when they ventilate the transformer that's in the electrical room next to the parking garage. And they pull the air out of the parking garage, because it's right full of car exhaust, dust and dirt and salt and everything else. And wow, you should see what it does to the inside of the transformer. You know, because all that moisture coming off the cars and it blows through there. So if the electrical room's next to a parking garage, pull the air from someplace else and blow it into the parking garage, because the warm air coming out of there, hey, it's going to warm up the parking garage. You're getting free heat, right? But don't do it the other way around. Yeah, rain and snow. Actually, there are transformers that I can get for you that we can put underwater. Literally submerge them. but they're like platinum plated and they cost you a fortune. So for most guys like this, rain, snow, entry into the transformer, you got to keep it out. And when you get dealing with the jungle utility gods, did my friend from Ottawa-Valley leave? Oh good, we can talk about it. So this is a representation of a hydro vault. Okay, so different utilities have different standards, but almost all of them have commonalities. And the commonalities are that when they have their equipment inside of a building, and I'm talking about inside of a building here, okay, they're going to control the room. They don't want other people going in there because it could have a negative impact on their system. So this is a representation of a hydro vault. These are transformers right here. And what does that look like in the wall right there, guys? What does that look like? Is it an exhaust? Or is it an intake? Either one. And it's sitting right over top of my transformer. So if there's not a rain hood or some other device to keep the snow and the rain coming in my service days I got called to an apartment building on Lees Avenue. They had an emergency. The emergency was that hydro had opened the door to the hydro vault, and there was a snowdrift about 4 feet deep in the hydro vault and had blown in, and the snow was building up inside of the transformers. So I got paid to shovel snow in a hydro vault that day, and then fix the electrical components that had melted from the moisture. So even somebody like a utility can show you stuff. This is taken directly from their standard drawings, okay? So when you're doing your thing, you're going to look at this and say, yeah, that better be an exhaust fan, right? And the intake better be, yeah, I don't know, looks like an exhaust vent to me. And then the intake better be someplace else. So we're not going to suck the vault full of snow and rain and moisture. Beyond your own guidelines for getting rid of heat, because you guys do this all the time, you know so many cubic feet per minute is going to, base that average temperature is going to get rid of the heat we need to get rid of. Great. The utility will have a number that is a lot higher. Find out what it is. They're very conservative, they like to overdo stuff like that. Okay? So despite the fact that I'm sure your calculation is absolutely accurate and you put a little bit of fat on it to cover it off, find out what the utility number is for the airflow rate through the vault and meet that requirement. Because if you don't meet that requirement, they won't turn your vault on. Which means delay the contract, which means changes to the fan, which means change order. Air conditioning. Yeah, okay, we're going to spend a bunch of energy on air conditioning to cool the room. I'm seeing this more and more. I'm seeing electrical rooms that are air conditioned. Now, I know there are two reasons for this. One, believe it or not, there are a bunch of unions out there that don't want their electricians working in environments where it's too warm. And apparently an electrical room that's like 75 or 80 degrees Fahrenheit is considered to be too warm, and the guys won't work in there. So they're air conditioning electrical rooms. But again, think about it. We've got to spend energy to get the heat out of the room. So I'm increasing my transformer size. If you don't have to, don't air condition the room, just use the outside air, okay? And honestly, heavy electrical equipment like this, it works just fine up to 40 degrees C. It's happy. It's designed to work at temperatures like that. Now, we don't want to go beyond 40 degrees C, okay, because then we have to derate the equipment. But the standard for the equipment is that it is built and designed to operate in temperatures up to 40 degrees C without derating. So it can get pretty damn hot in that electrical room. You're going to break a sweat. The other reason I'm seeing rooms air conditioned is because there is some electrical equipment, such as UPS systems, that won't work at 40 degrees Celsius. Okay? It gets pretty unhappy much beyond 25 degrees Celsius, and so we air condition the UPS room. All right? But try and avoid air conditioning the regular electrical room, because you just don't need to do it, isn't it?
We're good with humidity levels.
As long as it's not condensing, I don't care. If it starts to sweat, yeah, okay. I would actually prefer the room to get warm and avoid condensation, right? So if you got the big louver that opens up and you super chill the room down and the equipment, all the metal gets cold and it starts condensing and sweating on it, it goes boom. It runs over the surfaces inside and creates electrical tracking, and it literally goes boom. Air filters. Put them so you can service them. Remember, the electrical vault is controlled by the utility. Utilities like money. So if the filters are inside the room, first of all, you're going to have to call the utility to come unlock the door to access the filters, to change the filters. Most utilities give the owner of a vault like this one free door opening every 2 or 3 years. The rest of the time they charge $500 to $1,000 to come and do it. So you would know much better than I how often filters clog up. After that, you can't see the condition of the filter inside the room. So if the filter clogs and it restricts the flow of air to the room, and the room overheats because you've got 20 kilowatts of heat going inside that room with the 1,000 kVA transformer, it isn't going to be long before the high temperature alarm in the room's going to go off, and then the utility's going to show up, and they're going to shut you down until you fix the problem. And when I say shut you down, I mean turn you off, shut you down. Okay. So put the filters on the outside of the room. I'm still seeing this. I don't understand why. I'm still going to vaults and seeing somebody has put the nice little filter housing on the inside instead of on the outside where you can get at it. All right, we've done all the mundane stuff. Now we get to do the interesting stuff. The stuff that really matters to you guys. This is a 3-line representation of a motor starter. Cole's Notes version: contacts close, send electricity to the motor. Motor goes around, all the interesting stuff happens. The water gets pumped, the fan turns, all of the good stuff happens at that point in time. It'll start the motor, it'll stop the motor, we can change the direction of the motor. This little guy right here is a classic square D starter. It's about yay big. It would be good for, say, 3/4, 1.5 horsepower motor, okay? So, as the motor gets bigger, the starter gets bigger. Proportionally. So, big 500 horsepower motor, big 500 horsepower starter. Electrical, normally, frequently, mostly, because there's no laws or rules about this, specifies the motor starter when the motor is not part of the manufactured package. But does anybody here specify a chiller anymore where the chiller doesn't show up with the whole control package, with all of the starters and stuff built into the control package? You know, when I started doing electrical service back in the late 80s, I mean, you'd go into some places and there would be a honking big motor on a chiller, and then over here, you know, the chiller was made by York, and over here there would be a giant square D or Westinghouse starter to run that, and those two pieces of equipment were purchased separately. But the industry has changed since the 1970s, 1980s, and now most mechanical equipment comes with built-in starters, which means you guys get sucked into specifying this stuff. I suggest you talk to your electrical counterpart, because he can help you with that. He can make sure there are things in that specification that will make things work better for you, okay? And, you know, electrical guys, surprisingly, because I'm standing up here, we love to talk about what we do and show off our vast wisdom. So give the guy an opportunity to talk about it. You'll probably have a hard time getting him to shut up. Control features. Oh, man. I'll bet you this is launching more change orders than anything else. Especially where electrical has specified starter and mechanical's thinking they're getting something and they're not getting it. They're not getting a run contact that tells them the contactor's closed, the motor's running. They're not getting an overload indication contact to say that, hey, it tripped on overload. So there has to be a dialogue about who's specifying this and what do you need. Again, if electrical's specifying that starter, talk to them about it. And if they're not asking you questions about it, they're not doing their job. They should be asking you as well. It's a two-way street. Okay. When is part of the manufactured package? Electrical is going to ask you some questions. MOP, maximum overcurrent protection, which is basically what the manufacturer says, you have to feed my equipment through a fuse or a breaker of no bigger than this. Again, if electrical's not asking you for that, that's a big red flag, that's a big danger sign. Maximum operating current. What's the thing actually going to use? How many amps is it actually going to draw? MOP is always bigger than MOC. Sometimes not by much, but it's always larger. And typically, a cut sheet for a piece of equipment should have that on it. Yes, sir?
MOC, is that the same as MCA, FLA?
No, FLA is a little different.
Okay.
Full load amps for a motor. I mean, when I'm specifying the starter and you tell me that you've got a 10 horsepower motor and you send me the cut sheet on the motor, it'll have FLA right on it and everybody's happy, okay? The other MCA, yeah, they just use different terminology, okay? So it tells me what size I have to make the protection and how many amps is this thing actually going to draw. And we're concerned about what size we make the protection because typically that pre-manufactured piece of equipment only has conductors of a certain size in it. And if I make the protection too large, I'm not adequately protecting the conductors inside the unit. And then the electrical inspector opens the door and he looks in and he says, wait a minute, that looks like a number 2 wire. No, change the breaker. And again, change the breaker means change order. Drives. Everybody loves drives. Because drives make all your problems go away, right? Except for the problems that make themselves. Bigger the motor, the bigger the drive. Just like the starter. Operating a motor at less than 60% of full load speed, unless the motor is specifically designed for it, probably an overheat motor. So think about something else when you're doing that. It's also not very electrically efficient. Who specs and installs a drive? Well, it's just like the starter. If it's part of the manufacturer's package, like those really cool chillers they make now with all the different stages inside them, and they've got 2-pole motors that are turning at 3,600 RPM and all the rest of it. And I am so thankful I don't have to spec drives inside those packages. When it's installed inside our motor control center, and the drive is put inside the motor control center, the integration with electrical has to be huge. And I've done this, I do this, and I hate it because it just never seems to work out right unless you get the equipment manufacturer and the MCC manufacturer really tightly engaged with each other at shop drawing time. I always seem to have trouble with this. A lot of the time I've run into situations where a MCC manufacturer, Square D, the HVAC equipment manufacturer wants to use a Danfoss drive or wants to use an ABB drive or an Eaton drive. But Square D has got the MCC, so you've got a Square D MCC that somebody's putting an Eaton drive inside of, and Square D and Eaton don't like each other because they chase each other's business. And it just never seems to end well. Wiring should be by electrical, and electrical should be talking about that. And in a second, I'm going to show you how electrical should be talking about that. Mechanical considerations. VFDs are not perfect. They give off heat. So they need ventilated. And the lower the speed you run them, proportional to the power output of the drive, the greater the inefficiency in the drive, the higher percentage of heat it will put out. So if it's a 100 horsepower motor and you're running the drive at 65 horsepower, per se, it's not going to be very efficient. It will put out a lot of heat. It will put out a higher percentage of heat at that level. When it gets up to 100% efficient, it's generally a little bit better. All right. I think it's time for a new picture. That's hard to see. This is a motor control center with doors open. So essentially, it's sections that allows us to plug in what we call buckets that have starters and drives and all kinds of fun stuff inside. The electrical guys, we love these because it's an assembly. It can be tested in the factory before it comes to site. It shows up, it gets bolted onto a concrete pad, and it looks really cool. It's easy to install, it's fast to install, and yeah, it works really well. It also allows us to pre-wire for building automation systems, for fire alarm shutdowns, for a bunch of other stuff. So we love MCCs. So you're going to get pushed, especially if you have mechanical loads that are scattered all over the place, for me to do one electrical room, put an MCC in it, and run wire all over. It may not be the best solution for you, but it's the best solution for me. And this is where there's going to have to be a dialogue between you guys and the electrical guy about how you're going to approach that. Because for you, it may be better that there is a starter or a drive located closer to your motor. And you're going to find this indicated on the single line diagram. So if you, at the 30% stage, actually look at the single line diagram, you'll find the MCC indicated there, and then you go, I know what he's up to. I know what he's trying to pull. All my fans that are up on the roof 120 feet away, he's putting the MCC down here. I'm not sure I want him to do that. This is my motor schedule. This is what I use to specify starters or a motor control center. And I'm not sure how well you can see that, but this big legend down here is a list of all of the options that I can put on a starter or a drive for things like auxiliary contacts, handoff auto switches, indicator lights, auxiliary contacts. This is the shopping list of all of the features that we can put on a starter or a drive that will feed into your building automation system so you can get the information you need to properly operate that building. Frequently, not always, but frequently, I see mechanical doing some kind of schedule as well. And quite often, and I encountered it today, mechanical had a lovely schedule, and their schedule had all kinds of stuff about how electrical was going to do this and electrical was going to do that, and their schedule completely conflicted with my schedule. So we had to have a chalk to line the two schedules up. There is all kinds of stuff that is put on here about wired by, installed by, and the two schedules need to match each other. Or there will be all kinds of Question, here's a question over here. Did I get it? Yeah. All right. Motor starter. I frequently get questions about, we want to put something on the generator. We'll talk about generators a little more in a minute. This little graphic right here, especially this one in the corner down here, shows what happens when you start a motor to the current going into the motor. A direct start and a across the line start, where we just close the contacts, that current goes way high. Depending on the style of motor, it will go up to 11 times the full load amps. Now, it doesn't last very long, but it's a big inrush of energy to get that motor turning, to get that fan turning, to get the pump impeller turning, or the escalator moving, or whatever it is. So there's a huge inrush of energy involved when we do an across the line or a direct start. The bottom two lines, the blue one, is an old-fashioned auto transformer start or a star delta start. We almost never do that anymore because we got better tools. The better tool is a soft starter or a variable speed drive. And a soft starter is essentially part of a variable speed drive that controls voltage and frequency to start the motor off more slowly and reduce this huge inrush current. Now, the huge inrush current in a properly sized electrical distribution system is not a problem when you're connected to the utility, because the utility grid has Niagara Falls, Chats Dam, the 100-some-odd megawatts that are generated in the middle of the Ottawa River here, big nuclear plants, wind farms, solar farms. We generate terawatts of electricity. But a generator is one little internal combustion engine typically hooked to an alternator. So if I've got a 500 horsepower engine driving a generator, I can't start a 300 horsepower electric motor. Well, I can if I put a flywheel the size of a Chevy on there. And you can get machines that are built that way, but they're hugely expensive, and they're big, and they're hard to maintain. So when you come and you talk to me about putting loads on the generator, beyond the code requirements, which we'll talk about in a minute, one of the biggest issues I have is the size of the generator. Because it just has to be so much bigger than large motor load. If you're coming and talking to me about, well, we want to run the domestic water booster pump, and it's 50 horsepower, and I've got a 1,000 horsepower generator, the code issues to one side, I'm probably not going to have a problem with that. But if you're coming and talking to me about the chiller, which when the chiller is operating, it needs all these other pumps running with it, and its aggregate load of 700 horsepower, 750 horsepower, my 1,000 horsepower generator is not going to get that turning without some very special scheduling of equipment, starting motor loads one after another. Maybe not in the way that the system needs them started, because as I understand it, you have to start circulating the glycol before you start the chiller, or maybe it's the other way around, I don't remember. But the electrical guy is going to say, I want to start the big load first, and then start the smaller loads. And that may not work with the actual function of your system. So if the electrical guy says to you, oh yeah, I can start that for you, we can do that, okay? Make sure that he's taken into account the fact that he can't start it in any order he wants. He has to start those loads in the order that works for your system. And you have to make him understand that that's not optional. Because he's not going to know it. If I start too big a motor on a generator, I get a frequency dip, I get a voltage dip, and what can happen with that is the electrical loads on the system will drop out. The voltage will drop low enough that the coils, the magnets that hold the starters closed, the electromagnets hold the starters closed, will drop out. Okay? Then all the motors stop. That's not good. I have to look at, is the engine big enough? Is the alternator large enough? What's the response to the excitation system on the generator? And so it's not generally a question, when you're on the edge, it's not generally a question that your electrical guy can answer just like that. There's actually a whole modeling process we go through. I start too large a motor, I put too much of a step load on a generator, things break. And I've seen them break. Coupling on the back of the engine where it connects to the alternator. Makes a hell of a mess, explodes. So, quite often, I can't support a large motor load even though I've got a stupid, humongous generator in the facility. It's not a one-to-one relationship. Then there's the code stuff. C282 says, connected to an emergency generator, I can do fire alarm and emergency voice system. Firefighters' elevators and elevators serving stories above the first story in a high building. Fire protection water supply pumps. Smoke control systems, which is where you guys come in. You know, smoke extraction fans, stair pressurization, that kind of stuff. That can go on here, and I really need to know about that early on. Emergency lighting. Exit signs, because I want to get the heck out of the building at this point in time. That's it. I don't see chiller on there. I don't see domestic water booster pump. Now, I can supply them if my generator is large enough, but I have to be greedy. I have to put in a second transfer switch. It can be fed from the same generator, but it's a completely separate supply set up so that if that stuff we're supplying, the chiller, the domestic water booster pump, I don't know, the beer fridge in the building operator's room, whatever it is, if that load is in danger of taking my generator offline, it gets dumped. And we support the primary emergency loads first and foremost. They transfer first, they get first priority. So if you're called in to do a project inside of the building, and you know, the nice folks at the Congo say to you, well, we want to put our domestic water booster pump on emergency power, then your answer should be, sure, you got a second transfer switch. You got the second. Like literally, I did an evaluation in the building 2 years ago, and they couldn't figure out why their generator kept stalling. Every time we had one of those massive deluge rainstorms, went in and found out that all of the sump pumps in the building and the parking garage were hooked to the emergency generator. And when all those sump pumps ran at the same time, it overloaded the generator and the generator stalled. They said, well, of course sump pumps are emergency. No, sump pumps are not emergency. It's an asset protection thing. So we switched sump pumps to the second transfer switch. I hope you enjoyed your trip through the jungle. Questions? Lots of questions, I hope. Or everybody just wants to get the heck out of here to go home. Chris?
You have a diesel electric locomotive.
Yep.
And it's got oil tankers, kilometers of oil tankers. And you get locomotive on one end and one on the other. The torque that's involved in just getting that thing to start moving has got to be tremendous. And you said there's an example of a genset sort of breaking in the shaft or coupling or whatever. How would they do it to sort of make that possible?
Nasty question.
You want to separate Okay, you can.
So so with the locomotive, first of all, the locomotives are DC. Okay, so they control the voltage, and by controlling the voltage, they start off with low voltage to keep the current low, and they apply a slow, steady increase in torque. Okay, one of the things, and it's the same thing with the soft starter I was talking about, or the variable speed drive. We control the volts per hertz. Which basically means we're keeping the voltage low and we're changing the frequency at the same time to start it off slowly. It's like push starting the car. You remember push starting the car, okay? If the guy didn't put his foot on the clutch, you couldn't get the car moving. But once you got the car moving, you got the momentum built up, he took his foot off the clutch, well, you had the inertia built up. So yeah, two big locomotives, one pushing, one pulling. Well, both of them are starting off. They're not trying to accelerate that load up to the full train speed in the first 5 seconds. The fan in your ventilation system, when we hit it with an across the line start, that motor is trying to get that fan up to speed just as fast as it can. If we start it up slower, we can reduce the current, we can reduce the load. It's also easier on the drivetrain, I understand. Not quite the same shock. Good. Took me a minute to remember locomotives.
I know that motors big object.
Have you ever stood next to a locomotive when it was pulling the train out of the station? Well, I mean, they redline that engine, and then they start creeping the electric motor just the tiniest amount. So the engine, which is the source of power in this particular case, is going just as hard as it can, but then they're pulling it up slowly, more and more slowly. I did a project for Environment Canada. They had a facility, they had a whole bunch of dynos, and they brought cars in, and they put the cars on the dynos, and they were doing emissions testing, which meant putting the car on the dynamometer and running it for days. And the dynamometer was basically a big alternator that drove power back onto the building grid. And they had this idea that they were generating huge amounts of power, and that the department that ran the dynamometer should get a credit from the building for the fact they were putting all this power back on the grid. I got paid to, and I did the physical install, I got paid to install meters to measure the power consumption. This was 1991, 92, something like that. And so I learned a whole lot about dynamometers. Well, one thing about dynamometers is they have a whole bunch of cooling pumps and other things that work inside them to control the heat. And all those pumps use electricity. So when we actually measured the power that was going back onto the grid, simulating something like a pickup truck going down the road at 100 kilometers an hour actually consumed about 15 kilowatts of created about 15 kilowatts of electricity. And of that 15 kilowatts, and this is a level road, and of that 15 kilowatts of electricity, they were using 5 or 6 to run the dynamo. So, just like your train example, once you get it up and moving, it doesn't take a whole lot of energy to keep it going. And they got really mad at me and they said my system was crap. They threatened not to pay me, and I had to hire an outside expert, come in and do measurements and prove to them that all the energy they thought they were creating with all these vehicles was in fact going someplace else. Yes, sir?
Locked rotor amps.
Yes.
What does that mean? What is it used for?
Well, I get padlock in. So, locked rotor amps refers to two conditions. One, installed motor, okay? But it also refers to the condition when I first start the motor. When I'm first starting, before it starts to turn, that locked rotor amps is the actual initial kick of amps that's going in. So that would be the actual overload, that 7 to 11 times that I was talking about, all right? We also use it as when we're doing motor protection, we use that value because the motor manufacturer builds the motor to withstand locked rotor amps, the starting current that goes through, because it's a lot more current. So it generates a lot of heat as it goes through the conductor. They use that value to create a protection curve for the motor. So very large motors have a certain number of starts they can do in a period of time because they have to cool down between each start. So it could be measured in hours, it could be measured in days. I did a project with a 25 megawatt motor. The cool down on that motor was a day. You could start that motor once a day. That was it. We also had to call the local utility and ask them to put another coal-fired generator on to start the motor. But so we use it for protection, we use it for figuring out what the inrush is going to be, and making choices about the starting type.
So how does that relate to the disconnector?
So in the electrical code, I am required to upsize the current, the wires going to a motor by 25%. So if the full load amps on the motor is 100 amps, I have to size wires for 125%. In the actual pieces of equipment, there will be like a disconnect switch that's feeding a motor. You will see the disconnect switch will say 60 amps or 30 horsepower on it. So when it's applied as a motor, okay, the disconnect gets derated because at 600 volts, a 30 horsepower motor is using about 30 amps. For a regular load, I can use the same disconnect for 60 amps. Make sense? Yes, sir.
On a lot of residential, a lot of what you see motor ratings when you put ratings at 230 or 208 volt on 240
Okay, so 208 is a three-phase system, just like that 600 volt three-phase system I was talking about. So in the ratings, especially now that it is a rural electrical market, okay, you will see things that are rated at 240 volts because you can be using equipment in other jurisdictions that use different voltages than we do, okay? The thing to look at is it a 240 volt single phase motor or is it a 240 volt three-phase motor? If it's a 240 volt three-phase motor, that voltage reference there says it can work up to 240 volts and you're not going to have a problem with the insulation rating. Then there should be sub-ratings on there that talk about 208 volts. We need to get rated power at 208 volts. Okay? That's part of the reason that guys like me hate motors at 208 volts or 240 volts. We would like to get to 600 volts as soon as we can because it just simplifies the whole motor sizing issue. And we get odd motors coming out of different jurisdictions. Like I'm looking at a project right now where they've got some motor loads on there and they're 138 volts. It's some exotic equipment that's come from someplace. And I'm scratching my head and I'm looking at this and they've got special step-down transformers to supply this equipment. Yeah, that's going to take some digging and figuring out. And of course, that costs money. I suspect in this case, it's specialty equipment for a very special purpose. In other cases, I think motors kind of leak in from other jurisdictions because you can buy it on the internet for a really good price from China.
You see 208 / 240 single phase. You get 208 single.
Yes, you can get 208 volt single phase. So 208 or 240 volt single phase, the motor should produce the same rate of horsepower. Shouldn't be a problem on that. Okay. The amperage will be a little higher at 208, yes. Okay. So actually that's a really good question. This is that whole single phase versus three phase thing. The three phase diagram I was showing you, there's actually 3 wires coming to it. But we can create what we call single phase 600 volts or single phase 208 volts. And it's just a case of an electrical guy like me, you specify a unit heater. You've probably specified unit heaters at 600 volts when they're like 5 kilowatts, right? And the information will come to me, and I love 600 volts, especially for things like unit heaters. But it does not mean that that unit heater has 3 heating elements inside of it. It may mean that it just has the one heating element inside of it, and we're just putting 600 volts across the one heating element. So we're using 2 wires of our 600 volt system, and just to be pigs, we call that single phase. Yeah, I know. I didn't invent it, I didn't do it, but that's what it's called, okay? Just like 120 volts would be considered single phase, just like 240 volts would be considered single phase. So really what it means is, in that case, at 600 volts, single phase is we have the two voltage sources coming in. And quite often with new electrical people that are just coming into the business, somebody will come in and say, yeah, we're going to use 600 volts two-phase, because they've looked at the two wires that are coming into it, each with 347 volts on it, and they've decided that's two-phase. Yes, sir?
Can you tell me historically why cannot the U.S. don't standardize on some?
I can.
You can?
I can, absolutely. Because each country, as we electrified, each country tried to create a domestic electrical equipment industry. And they made deliberate differences between their adjacent countries so that you could not use equipment from country to country. It's the same reason that we're 60 hertz and other places are 50 hertz. Europe uses 400 volts. Single phase of 400 volts like they use in England is 240 volts. And they use 240 volts in place of what we do with 120 volt. So by creating these different ratings, you could ensure that your domestic electrical industry had a captive market. Because once you create a utility grid, you're stuck with it.
Now, who thought about that? How long ago was that decided?
I don't think I can point at any one person that decided and say that they did this on purpose. But I don't believe manufacturing protectionism is a new concept. So it wasn't one person that made the decision. But if you want to read some really cool stuff, go read about Thomas Edison and Nikola Tesla, the battle between DC power and AC power. I mean, there was literally a fight between Westinghouse Corporation and General Electric Edison Corporation on what we were going to standardize to. Obviously, AC won out for a bunch of good technical reasons. Yes, sir?
Further to that, I mean, being that we are so heavily influenced by the American HVAC market, I have had suppliers indicate that they either can't get equipment at 600 volts, and that's fine, or the worst one I think is we can get it at 600 volts, but not to meet your schedule, so therefore we will offer you a 480 volt piece of equipment, but don't worry, we'll give you a step-down transformer. Speak to some of the long-term implications.
If your step-down transformer is a 50 VA doorbell transformer, I would not hesitate at all in doing that. But remember what we were talking about heat losses from a larger transformer? So if you're dealing with, say, something that's got 100 horsepower motor in it, that I've got to put like a 150 kVA transformer to operate it, and it's wasting 2% every hour of every day, of every week, of every month, of every year, your client is now paying for wasted energy that they didn't have to pay for. And over the lifetime of a transformer and a piece of mechanical equipment, you know, forgetting the capital cost, because you got the transformer for free, right? Okay. Forgetting the capital cost of the transformer, the cost of the energy wastage, and getting rid of that heat energy, and the space that's occupied by that transformer that is not available for use for other things, and the maintenance on the transformer, because it should be looked at every 3 to 5 years, turn it off, open it up, clean the dust out of it, tighten all the electrical connections. If you could avoid having that transformer, you're going to over the cost of ownership. I mean, from a design standpoint, the electrical guy goes, that's no problem. You know, if I knew about it beforehand, if I could allow for it, it's no problem. We got room to put it, it's no problem. But the person who's going to suffer is the end user, the owner. And they're going to suffer. Yes, Chris?
Transformer, say an electrical one, is there a cutoff point in terms of ones that are paying and ones that want to just put on the floor plan?
After 75 kVA, they get pretty heavy. Depends what you're hanging in the front. Like I've got a client where we've hung a bunch of 112.5 kVAs, but they have a really strong structure up there. The structural guys took care of it for me.
So it's really just a weight issue then, it's not a descriptive thing, an electrical code?
Well, the electrical codes push back on a number of issues in that regard. One of them being we now have to put bottom in the transformer, because when a transformer fails, it likes to crap sparks all over the place, and they want a bottom in it so it doesn't rain sparks down on somebody walking underneath. But I mean, the big thing is the structural weight, and then the seismic considerations that have to go with the fact that you've got something that weighs 2, 3, 4, 5,000 pounds hanging from the ceiling. Yes. Yes. But I love hanging transformers because, I mean, floor space is so expensive. Other consideration about transformers, and it doesn't impact you guys so much, is that we try and stay away from anything bigger than for the 600 down to 12208, we don't want to get bigger than 112.5 kVA, because then we start running into arc flash issues and other stuff. So if you've got if you specified a 12208 volt air handler that needs 400 amps, and the cables get it.
Quality of the transformer, in terms of, is there a higher level or less noise or less problem?
Well, it depends on what you mean by noise. I'm assuming you're talking about this kind of noise.
I was thinking
Pollution, like harmonics. So yeah, we have special transformers that have features in them that help to attenuate the electrical pollution created by certain switching power supplies and keeping it going from back out on the grid. Okay? We use those in data centers a lot. Transformers are heavier, they have bigger cores, they're more expensive. I'm not sure if they're less efficient. I think they're still, I mean, they're still very, very efficient. But reliability-wise, incidentally, transformers are amazingly reliable machines if they have a decent atmosphere working. We talk about a failure rate of 1 in every 300 years of operation for a transformer, if it's in the right environment. We sort of exclude the fact that somebody poured 5 gallons of water on it or something like that. That's not regarded as it's an induced failure, not a natural failure.
for electrical reasons, you know, put the clause like that, you put a drip shield on top of it. Is there any place where you could eliminate the sprinklers, whatever, just because of the risk of the water going in it? Or, I don't know, more mechanical than electrical?
My attitude on that has always been, if there's a fire in there, I think we should put it out. Because my little dry type transformer is a hell of a lot cheaper than a building or somebody's life, you know? And if I've done my job right with the protection, when the sprinkler water goes into the transformer and it shorts out, the breaker's going to turn off. And the system will isolate itself. And yeah, you've got a repair job, but it's not nearly the repair job of the building burning down. Yes, sir.
If you're changing out a chiller that's a medium rather than 4,000, and you're going to something that's a 600 volt, is there a better way to do it than a transformer in the room, like from the hypervolt and pull the 600 volts from there, or is that just not
That's a really, really broad question. If you're telling me you've already got medium voltage in the room, in the building, 4160 volts in the building.
Yeah.
I mean, you can, the breadth of the question is so large, I can't give you a one-size-fits-all answer. It may be appropriate that, yes, you could upsize the 600 volt transformer in the vault and avoid another transformer. But then when you upsize that transformer, you increase the available fault current, which then could cause all of your other equipment to become inadequate. You wind up changing the whole distribution. One of the things I love to do personally in similar situations to that is to see if I can get that transformer outside. Feed the transformer, but then put it a pad mount transformer outside adjacent to the building, so I don't have to get feed out of the building. I'm not using floor space in the building, but still keeping it close because the cables are going to get much bigger at 600 volts.
Yeah, the transformer at 10 to 1, almost 10 to 1, it's huge, right? But conversely, the opposite question, if there's a 600 volt chiller and it's of the size where a 4,000 volt chiller is available, like, is it really beneficial to go to the 4,000 volt chiller?
If you have 5 kV, 4160 volts available in the building, and then there's a bunch of other questions that have to get answered from you mechanical guys on the end about how that chiller is going to get used. Okay? So that assumes that you already have the 4160 volts it's there. Most buildings don't have it. The one caution I would use on that is that I'm actually seeing it mostly going the other way. Most owners of facilities want to get rid of medium voltage unless there's a real pressing reason to keep it, because they're not comfortable dealing with it. And finding contractors who want to work with it continues to get more and more difficult.
And the best way to handle a transformer, you say?
I'm sorry.
And the best way to deal with that is to handle a transformer?
Too broad, too broad. You know, the best way to deal with your wife being mad at you is to always show up with diamonds. I didn't see any of the ladies nodding their heads. Come on, you know, I know my wife would. So, but you know, you're asking for best, and there's no one size fits all in that regard. And this is where working with your electrical colleague can really help you to make those decisions. I mean, I try and avoid transformers if I can, but in the chiller world, I mean, I'm seeing you guys do things with chillers. I used to see chillers that filled huge rooms. And then I walk into the room and there's this little chiller over in the corner, and I'm going, this is doing the same job as that monster? I mean, in a lot of cases, it's just the change in size of electrical load for a modern chiller is so dramatic that I might be able to go to the existing 600 volt service and supply it.
I'm more in the residential market, not the big building market. In my house, I have it equipped so I can measure the wattage of every single appliance, except the 240 volt appliance.
Yeah.
What's the easiest way and cheapest way to measure the wattage used by
A 240 volt appliance?
Yes.
So most 240 volt appliances, like your dryer, your oven, your stove, measure one way, measure 120 volts on one side, and then multiply it by 2.
Is that right? Yeah. So I could stick by a lot paper on only one of the phases.
You could get an electrician to come in and do that. Because I can't tell you to do things like that because we want to see you here again, and I'm sure you're perfectly competent and all that stuff. But yeah, we quite often will measure one leg on a resistive load like stove or a dryer or something like that.
Hook to one of the phases.
Yes, and just multiply the power consumption by 2.
If I do both phases, it'll blow up bigger than that.
Probably. I don't know what meter you're using, but we'll measure one phase of the 240 volt, multiply it by 2, and I get my power consumption.
And that's what works.
Yes. Yeah.
I think we'll do one more question, and then people can just ask.
Oh, yeah.
afterwards.
Okay, look, I'll do one more question now, and then while I'm packing up, come and talk to me, okay? And you've already asked a question, so gentleman in the corner.
So this is the AC/DC discussion, and more of a question about electric shock and why is it AC hurts. And I'm talking from being a child guinea myself in this experience. Why does AC hurt so much more than DC?
So I've raised 5 sons, and I think every freaking one of them stuck something in an outlet. So your dad is someplace going, you just stuck something in an AC over the sine wave starts off at 0 volts, goes up to a peak voltage, comes back to 0 volts. Okay? DC is a steady state voltage. The pulsing effect of the AC triggers your muscles. It causes the nerves to fire. It causes your muscles to contract and lock on. So when you get an AC shock, and I've had some substantial AC shocks in my service career, it will cause your muscles to lock. You can't let go. And the muscles are being overfired, and they're literally trying to tear themselves apart. You've torn a muscle when you were exercising. You put micro tears in your muscle. Well, the AC power is so overstimulating the muscles that they're literally tearing themselves apart. Now, DC just passes the current through you, but it's not changing in voltage, so it's not stimulating the muscles. So all it's going to do is burn you. Burn you pretty bad, but that's all it's going to do is burn you. So the current will pass through, it will pass through the electrolytes in your body because they make a good conductor. And since you are a resistor, current passing through a resistor, you turn into a heating element and it will burn you. But because your muscles are not spasmed, you can go and let go of it. AC, right shock, and I know this from personal experience, you can't let go.
So the local threshold where it will actually do damage, you say that DC is somewhat safe.
So why I'm smiling, okay, I hope I don't have too sensitive listeners, is when Westinghouse Corporation and Edison Corporation were fighting over AC versus DC. What Thomas Edison had a traveling roadshow with a little alternator to make AC, and he would go to the local dog catcher, get some dogs, and he'd electrocute them in front of people. And then he would hook the same dogs up to DC power, and it would make the dog howl and cry and all the rest of it, but all it would do is burn them, okay? Whereas, so he was demonstrating the fundamental lack of safety in AC power in an attempt to create a market for his DC power system. Okay? So, yes, you can say that DC power has advantages in that regard, but I can also create AC power systems that won't give you a shock. We do it all the time for surgeries and emergency wards and critical care facilities where we create special AC power systems with special monitoring on them. Good example would be the receptacle in your bathroom in the base of the sink. There's a ground fault circuit interrupter. And that ground fault circuit interrupter will protect you in the event that you drop your razor, your whatever, wife's mad at you, she throws a toaster in the bathroom. And it turns off fast enough to protect you. We've also created what we call an arc fault circuit interrupter. And an arc fault circuit interrupter is a device, a breaker, that can tell the difference between a normal electrical load and an arcing electrical load. When you shoved the scissors in the receptacle when you were a boy, my son Sam did it created a spark. And the spark started to jump in there and it created an arc, just like an arc weld. Now the problem with an arcing fault like that is that a regular breaker, if the current flowing through that fault is below the threshold of the regular breaker, it just sees it as a load. But it has a particular characteristic that an electronic device can measure. And we've learned how to measure it. And we now use it to turn off the breaker. And the big driver for this, it took us decades to get this working. The big driver for this was, just like you as a child, when you shove something in a receptacle, was it in your bedroom? Maybe. I know it was with my son. And what they started to track was the number of children in North America that were being burned, and I mean severely burned and killed every year by shoving things in receptacles in their bedrooms. And so the industry worked over time trying to make this work. They had a few false starts that didn't work. And we now have it in place, and the electrical code all across North America requires for a sleeping chamber in new construction or renovation, you will use an arc fault circuit interrupter. So what we've noted, what has been tracked and has been proven, is that the number of children that are suffering severe burn injuries associated with shoving things in receptacles has declined remarkably. It's a real good news story. So the long answer to your question is AC power can be made every bit as safe as DC power. Like anything else, it's just how we handle it, what we do. Folks, thank you. You've been a lot of fun. I appreciate your participation.
Thank you very much, Jeff. I mean, the questions that just kept on going, I mean, I think that just shows the interest and the need for this discussion. We would like to present you with a counter coin from the Mint. It's
the picture now?
It's our pleasure to have you here. Thank you very much.
Thank you. Awesome.
direction this year, sort of, for future years. I mean, really, we're trying to tailor this to you guys, and that feedback is imperative. The next month's meeting will be back here at Centurion, and I thank everybody for coming, and hope to see you next month. Thank you.